Okay, let's continue our treatment of simple harmonic motion by thinking about the energy considerations. And then after examining that, that will give us some inspiration to take a look at an analogy to rotational motion. And this will explain why it is that we not only use omega as the symbol for angular velocity, but also the symbol for natural frequency. So with that, we'll go ahead and remember that our system is a mass on the end of a spring. And so the potential energy is 1/2 kx squared. So if we remember from before, we can say a lot about the motion just from that. I can go ahead and plot the potential energy. So this shape here for the potential energy is some kind of parabola. So it's known as 1/2 kx squared. And if you remember from before, we could find the turning points of the motion by plotting the total mechanical energy, E. And where we intersected here and here were the turning points. So the turning points will correspond to at plus and minus the amplitude. All right. And we can also remember that this is a restoring force. Remember that the x component of a force is minus du dx. Technically, it's minus partial u partial x, but I'm not making a big deal about the distinction here. And so we can go and look at, say, this point right here as an example. If we strike the slope of the tangent line here, we see that we have a positive slope. Since the force goes as the negative of the slope here, that's going to say that anywhere to the right here, where the slope is positive, we will be feeling a force back to the left. And by the same token, if I pick a typical point here, the slope here is, of the tangent line here, is negative. So that means that the force will be positive. So we always have the force pointing back in towards the middle, which is what makes this a restoring force. It always points back to the equilibrium position. All right. So we know that whatever is kinetic, whatever isn't potential is kinetic here. So I can go ahead and start plotting the kinetic energy. Like so. And the sum of the potential and the kinetic always has to be equal to the total mechanical energy at all times. And we can see here that the kinetic energy would, in theory, go negative if we went out past the turning points, which that isn't possible. All right, now can we start to think about what the potential energy would look like, and the kinetic energy for that matter, 1/2 mv squared, as a function of time? Well, sure we can. If we remember, we said that the position as a function of time is equal to a cosine omega t plus phi naught, and the velocity as a function of time will be minus omega a sine of omega t plus phi naught. All right, so the potential energy then as a function of time would be me putting in the position function into this. So this would be 1/2 k a squared cosine squared of omega t plus phi naught. And by the same token, the kinetic energy would be 1/2 mv squared. So this will be 1/2 m. Then squaring the minus sign gives me a plus. Squaring the omega gives me an omega squared. Squaring the a gives me an a squared. Sine squared omega t plus phi naught. All right, let's go ahead and check whether the total mechanical energy is conserved. So the total mechanical energy, remember, is going to be U plus K. This is 1/2 K A squared cosine squared of omega t plus phi naught plus 1/2 m omega squared A squared sine squared of omega t plus phi naught. However, we remember that the angular frequency has to be equal to the square root of k over m. So that means that omega squared is equal to just plain k over m. So I'm going to make that substitution in right there. So then this gives me 1/2 k a squared cosine squared omega t plus phi naught plus 1/2 m times k over m a squared sine squared omega t plus phi naught. Well, for small favors, the m's cancel. Now, both terms have a 1/2 ka squared in front of them, so let's pull that out. 1/2 ka squared. Now I'm left with cosine squared omega t plus phi naught plus sine squared omega t plus phi naught. And you look at that and go, wait, that if we remember from trig, sine squared of some angle plus cosine squared of the same angle is always equal to 1. So no matter what t is, at all times, the phase inside cosine squared and the phase inside sine squared is going to be the same. So everything in the brackets is just a really fancy way of writing the number 1. And so we get that the total mechanical energy of the system is, the total mechanical energy of the system is 1/2 ka squared, which makes sense because that is the potential energy at maximum stretch. But it also doesn't depend on t at all. And so sure enough, energy is conserved, which is a good thing. But now taking a look at that, seeing this sine squared plus cosine squared thing here, should be maybe getting your creative juices to flow a little bit and think about circular motion. And you would be correct. And so this is where the rotational analogy to simple harmonic motion comes in. And this rotational analogy is going to make its way back a few times in later courses. Rotational analogy. This will get redressed up a bit when you study electricity and magnetism. When you're doing AC circuits, you'll call this phasors. And phasors get used a lot in other kinds of engineering analysis. And then physicists will take it in a little different direction as they go on into further courses, and they will turn this all into basically circular motion in the complex plane and do some fun tricks with Euler's identity. But we don't need to get into the weeds of that here. Just trying to show you why it is that we use omega for both. So the idea goes like this. If you take a mass on a string, and this is something you can totally do at home, like take a tennis ball or something like that, tie a string to it, and then set up a really strong light at the opposite end of the room. And then what you want to do is you want to swing the ball vertically, or horizontally, either way. You want to swing the ball around in a circle, like so. Boop, 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 like that. And the idea is that way off over here, you have your light. So we're casting rays of light like this. And then if you look at the wall behind you, you will see the shadow of the ball. So we'll just mark this as the shadow of the ball, or the ball's shadow. Now, what I'm going to assert is that if you look at the motion of the shadow of the ball, the motion that this ball's shadow makes is simple harmonic motion. Where it'll go as our cosine. So the reason for that is, let's go ahead and drop in a coordinate system so we can think about this a little bit. Like so. So then if we, again, just doing my usual thing when I'm thinking about these things, I set phi naught equal to 0. But all that's going to do is change the initial angle that we're starting at here. This angle right here, phi, or sorry, theta. Actually, it can, we'll just write as omega t plus whatever our initial phase is. That is the current angular position of the ball. Now, what is the position of the shadow? Well, that's going to be this bit right here. So this angle and this angle are congruent by alternate interior angles. And this length here is my x-coordinate, x of t. So if we say that the radius of the circle is the amplitude of my motion, then this is going to be this radius here times, since this is an adjacent, the cosine of this angle here, omega t plus phi naught. But we can take this even further. We can think about the velocity of my ball. So here I'll go ahead and draw my velocity vector, like so. And since this is a tangential velocity, it's got to be equal to the radius times the angular velocity of the ball. Well, we can find the angular velocity of the ball. I differentiate this with respect to time. Oh wait, it's omega. So this is a omega. All right. And then here, this bit here would be the x component of the velocity, which would be the velocity of my shadow. So actually I'll say v tangential here, because my shadow's velocity I'm just going to call v. So v here will be equal to v tangential, and I'll have you think about it in all four possible quadrants, but in each case you can convince yourself that you need to have a minus sign in front of there. This angle is this angle here. This angle and this angle are this angle here. Because this makes up 90 degrees and that makes up 90 degrees, so those have to be the same for that to work out. But that's going to make this the opposite, so this is going to be sine omega t plus phi naught. But we said that our tangential velocity was a omega, so this is minus omega a, just to get in the form we've seen before, sine omega t plus phi naught. And I think you can guess where this is going, but now let's do this for the acceleration. My acceleration vector is going to point like that. And again, the acceleration of the ball is just going to be the x component of it. So a sub x is what I'm going to call a here. But that's going to be the x component of the centripetal acceleration. But the centripetal acceleration is the radius times omega squared. So again, we have a minus sign because this is pointing to the left when my position vector is pointing to the right. So I'll have A equals minus the centripetal acceleration, and we're back to this being an adjacent, so it is a cosine of my angle, omega t plus phi naught. So this will be A equals minus omega squared A cosine omega t plus phi naught. So it turns out that the motion of a mass on a spring is exactly the same as the motion of the shadow of a ball that is going in uniform circular motion. So because this analogy is exact, this is why we use the notation omega for the for the natural frequency, because of this one-to-one identification with the angular velocity of the mass on the string. Alrighty, going forward here, we're going to pick up by taking a look at the general simple harmonic oscillator and applying it to specific cases. So we'll see you over there.